one of these days I need to say something really, really important in the first 5 minutes of class. The magic word is bacon. So on the midterm, when it says, what is the magic word? You write bacon. And it says, how are we supposed to know that? I said, well, I said it in class. You weren't here. Sorry. Okay, so administration stuff. This is the last lecture on material that will show up on midterm 2. Starting on Thursday, we're going to be shifting gears again and starting in the third main chunk of the course, which is instead of showing that things are, we know how to do things, things are so easy that even we can do them, we're going to show that things are hard, and eventually we're going to show that things are impossible. But this is going to be it, to the lecture today and the lab tomorrow in terms of covering the material for midterm 2, which will be held a week from Thursday after everybody's gotten a chance to work on homework 8 for a week. The architecture of the exam is going to be exactly the same as last time, 5 questions, one of which may be a sort of true-false, multiple-choicey kind of thing, and then four other kinds of questions. And in general, the same time constraints apply. So in terms of the kinds of questions we might ask, we can only ask you things that we can reasonably expect most of the class to do from a cold start in 15 to 20 minutes. Including writing the answers down. So a lot of the things that show up on homeworks are a lot bigger than that. Later this week, I'll put up a form in case you need to sign up for a conflict exam. The conflict exam will be on Friday. This time, I believe Friday is not also a religious holiday. And if there's any way to do it, the only conflict exams will be on Friday. But I'll have the sign-up form for that up in the next day or two. And we're also, as I was just reminded before class, working on collecting a bunch of practice problems, mostly from old exams, so that you get a better sense of what kinds of questions we think are fair to ask. All right. So the last thing the last algorithms thing that we need to talk about is, well, we have this list of problems that one might want to solve on graphs. The very last one was computing shortest paths. Now, the first word that probably pops into your head, because you're all good computer scientists, is Dijkstra. For those of you who don't remember how to spell Dijkstra, there's 3 nested loops in the middle of his name. IJ is actually more or less a single letter in Dutch. It's sort of the same as you umlaut, except it's pronounced I. It really is pronounced Dijkstra even in Dutch, not Dijkstra or Dijkstra or Dijkstra or whatever. But this is not the end of the story, right? Dijkstra's algorithm is not the only algorithm that one can use to compute shortest paths, nor is it the best algorithm to compute shortest paths all the time. It's useful for a very common but still fairly restrictive special case, which is, the sort of 2 axes here that I want to distinguish between. There are 2 shortest path problems. Now, what I'd actually love to be able to say is, in fact, there are 3 shortest path problems. you have two nodes in a graph and you want to figure out the shortest path from one to the other. The only problem with that is we really don't know how to solve that problem directly without solving one of these other more general problems. There's the single source shortest path problem, where you have a source node S, and you want to compute shortest paths leading from S to every other node in the graph. And these shortest paths are necessarily, as I'll prove to you in a second, these necessarily are going to form a spanning tree of the graph, assuming the graph is connected enough. It'll form a tree. Okay? So Dijkstra's algorithm computes single source shortest path trees. Okay? It computes the shortest path from S to every other vertex in the graph. So it's not single source, single target, because we don't know how to do it without solving this more general thing. All pairs shortest paths is essentially the same problem, but where S is every vertex. I'm going to compute for every pair of vertices S and T the shortest path from S to T. So this is one source, all targets, and this is all sources, all targets. And as I said, the one source, one target, we don't know how to solve except by doing one source everything. Okay, so Dijkstra's algorithm works for single source. You can also use it for all pairs by just running it at every source, but that's not, in fact, the fastest algorithm, at least when the graphs are fairly dense. One of the other conditions, though, that needs to be brought in, so remember that what the input to the shortest path algorithm is, in both of these cases, the input is a directed graph with vertices V and edges E, and a length function, sometimes also called the weight function. I'll just call it W, from the edges to, I don't know, the real numbers. So you're given a directed graph where every edge has associated with it a weight that represents the length of the edge. Now, there are two possibilities. One is all weights are non-negative. The other is some weights are negative. Right? Now, when you're thinking, if you want to think of these as actual lengths, distances on a map, for example, it doesn't make any sense to think about negative lengths. But there are other circumstances where the weights on the edges don't represent distance, but represent some other quantity. They might represent the likelihood of something, or they might actually represent the cost of traversing an edge. So I could imagine, for example, that there's a network of toll roads, and it costs me a certain amount of money to drive from one place to another. But there are a couple of roads that, somebody who's going up for re-election really wants to show off. And so if I go along this road, actually you go up to the toll booth and they hand you a $5 bill and say, vote for Jim. Right? I mean, it's a farcical example, but if you're imagining, trying to drive network traffic around the internet, it may not be so far-fetched to imagine that fledgling ISPs actually might want to attract network traffic to their network as opposed to others, because then they can say, look, we're not Comcast, we don't throttle Netflix. And we'll actually pay you to route your traffic to us so we can show you off better. Dijkstra's algorithm only works for shortest paths, single source shortest paths, when the weights are non-negative. I should say only works. Depending on which version of the algorithm, it either only works in the sense that it only gives you the correct answer, or it only works in the sense that it's fast only under these conditions. The version of Dijkstra's algorithm I'm going to show you, it always works. It's just sometimes it's slow. the version of Dijkstra's algorithm in almost every textbook and on Wikipedia. If there's a negative edge length, it just gives you the wrong answer, which I think is stupid, but whatever. I can't just go and change Wikipedia because that would be original research or something. I don't know. Also because everyone would just change it back. Because this is what it says in CLRS. And why does it say that in CLRS? Because it said that in Hopcroft and Ullman. And why did it say that in Hopcroft and Ullman? Because, well, because that's what Knuth said. And why did Knuth say that? Because that's what Dijkstra told him. Dijkstra was a bit confused about his own algorithm. It will actually work when some of the weights are negative. You just have to write it the correct way, which is weird because Dijkstra was all about showing that things were correct. So how do these things actually work? So the first thing I need to convince you is that, in fact, shortest paths define a tree. But the zeroth thing that I need to show you is there's actually, some conditions that show up specifically when you allow negative edges that we want to be able to avoid. I can't just say, okay, all edges are negative, now what happens? Because there's this weird side effect that shows up, right? Which maybe I have a graph that looks like this. Right, so here's a graph, and one of the edges is negative. Okay. Now, if I want to imagine that these nodes represent planets that I'm flying to from one to the other in my TARDIS, and the numbers are the amount of time it takes to actually get there. Yes, there's a negative 12 up there because, like I said, I'm flying a time machine. And the question is, how quickly can I get from the planet on the left to the planet on the right? Meaning, if I leave the planet on the left at January 1st, 2000, how soon can I get to the planet on the right? And the answer is, there is no answer, because I can just fly around this loop as many times as I want. Each time I go around it, I go 2 years into the past. And so in this sense, there is no shortest path from the vertex on the left to the vertex on the right, because any way that I want to go from the left to the right, I can make it shorter, meaning I can decrease the total length of the walk by going around that cycle one more time. Okay? So negative cycles are bad. Okay? Now, for purposes of this lecture, I'm just going to assume that negative cycles don't exist. The input is given to you in a way that is guaranteed not to contain any cycles of negative total weight. In the homework, I'll actually ask you to poke at that assumption a little bit and try to figure out, how do you actually figure out when a negative cycle is there and when it isn't. But for now, in the interest of time and keeping things simple, I'm just going to say there are no negative cycles. Shortest paths are, in fact, well-defined. And they are, in fact, simple paths. They don't go around in loops, because if there's a loop, its cost must be positive, and so I can get rid of it. Okay. Now, the second thing, the first thing now I need to show you is that shortest paths define a tree. And the way I'm going to do that is I'm going to argue by contradiction. Let's suppose that I find shortest paths from S to U and shortest paths from S to V, and they don't glue together the way you would expect a tree to behave. That thing in the middle there isn't a cycle really, because it's the arrow, half of the arrows are pointed the wrong way. But if you ignore the arrows, if you ignore the directions on the edges, the union of these two paths is not a tree. It's something more complicated. Okay? So I'd like to argue that this can't happen. okay? That shortest paths can't ever have this kind of structure where they diverge and then reconverge again and then go off to their separate destinations. Unfortunately, I can't really argue that this never happens. I have to make a weaker claim, which is there is a collection of shortest paths from S to all the other vertices that define a tree. Okay? Now, the proof of this is, look at the following. You know, the length of this purple path from S to V, this is the weight of S to A plus the weight of A to B plus the weight of B to C plus the weight of C to V. Similarly, the orange path is the weight of all the orange edges put together. Now, the nice thing about shortest paths is that subpaths of shortest paths must themselves be shortest paths. So this purple path from S to B must be a shortest path. Because if it weren't, I could swap in a different path from S to C, and then that would give me, by gluing on this edge, a shorter path from S to V. Right? So this must be, you know, the shortest path from S to C. But by exactly the same argument, the orange path from S to C must also be a shortest path. All right, so here I have a different shortest path from S to C. And so I can say, well, look, I actually have two shortest paths to the same vertex that have the same length. There's a tie. Now, unlike minimum spanning trees, there isn't a systematic way of breaking ties like this that is straightforward. But as it turns out, you can just say, okay, you know what? I'm going to just edit this orange shortest path. I'm just going to make it go up along the top. Instead of running through D, I'm going to go through B. Now I've found a different collection of shortest paths that has one less bubble in it. Right? And if I do this for if I do this kind of modification for every pair of shortest paths that diverges and reconverges again, I'll eventually transform the collection of shortest paths into a tree, right? Without changing their lengths. Okay. So I can't argue there's a systematic way of choosing, you know, canonical shortest paths, but what I can argue is there is a set of shortest paths from S to every other vertex that define a tree. And they're not the only shortest paths, but I can. So what this means is that if I build an algorithm that looks for a tree, I will actually, you know, it's possible that I can actually get the right answer. I can actually get shortest paths out of it. Okay? And this is, in fact, what all shortest path algorithms do. Yes?
Wouldn't you need to leave in your path in A to B?
Oh, yeah, right. I'm just, yes, the eventual shortest path tree that I build would also have to include a shortest path from S to D. And so maybe this edge would stay put. All I was saying here is I'm going to change the shortest path, which shortest path I return from S to U to go through the vertex up here at the top instead of the one at the bottom. Okay. So how do I represent the shortest path tree? Yes, I'm sorry. There's another question. So in an undirected tree is a connected graph without cycles. When I say a tree here, I mean think of an undirected tree and then orient all of the edges away from S. So it's a rooted tree with S at the root. Okay. So the way that we represent this in sort of basically every shortest path algorithm is I'm going to maintain two fields at every vertex. Okay, one of them is called the distance, and one of them is called the predecessor. distance, and eventually the idea is this is going to be the shortest path distance from S to V, and this is going to be the predecessor of V on the shortest path from S to V. Okay? This is what I'm trying to actually compute. Now, at the beginning of the algorithm, I don't know what the distances are. That's what I'm trying to compute. And I don't know what the predecessors are. That's what I'm trying to compute. But at the end, once I have this data, this is enough to encode all the shortest paths from from S to everything else. The predecessors are really parent pointers in this rooted tree. Okay? So I'm not storing for every node V, the explicit sequence of edges. I'm collapsing them together a bit into this more compact representation. Okay, now, generally speaking, I'm going to imagine writing the distances by putting them at the nodes themselves. And I'll represent the predecessors by some other means, but I want to show you one example of sort of an intermediate state in a shortest path algorithm that shows you how every shortest path algorithm makes progress. Suppose in the middle of my algorithm I discover that the node on the left has a distance of 5 and the node on the right has a distance of 8. But the edge in the middle has a weight of 2. What can I immediately conclude? Can that 8 possibly be the right distance? No. Well, one of these are wrong. One of these distances is wrong, right? And I'm going to guess it's probably the bigger one, right? And the reason is, whatever shortest path got me to this node, which had length 8, there's a different shortest path which goes through this node on the left that has length 5 plus 2. Right, so I can change the distance to 7. Then I can change the predecessor, instead of whatever it was, I can change the predecessor to be the node on the left. Okay, so I'm going to say that V is tenths if the distance at V is bigger than the distance of U plus the weight of the edge from U to V this is when the edge from U to V is tenths. Okay, so that edge too can sort of look at its two ends and say, this is bad, this is horrible, this can't be right, someone is wrong on the internet, I have to correct it. Hey, you guy at my head, the guy at my tail says he's only 5 away and I only have length 2. That means your shortest path should go through me. It may not be correct, but it's certainly better than what you're doing now. Okay? And so there's a subroutine that almost every shortest path algorithm uses called relax, which is, let me change the predecessor of V to U, and then let me change the distance at V to be the distance to the predecessor plus the weight of the last edge. Okay? So here is almost every shortest path algorithm. Initially, you know nothing about the distances and the predecessors, so I want to at all times maintain the invariant that my distances, they may be incorrect, but they're incorrect by being too big. So I'm going to start out initially by saying all the distances are infinity, except at S, where I know the distance is actually 0. I know the shortest path from S to itself doesn't go through any edges, and therefore has total length 0. Okay? So the generic algorithm is the following. Distance to S is 0. For all vertices that are not equal to S, The distance to V is infinity. And then for everybody, you know what? You don't have a predecessor. Okay? The source vertex is never going to have a predecessor because there is no last edge on the shortest path from S to S. The shortest path from S to S doesn't have any edges. The other predecessors are undefined, not because there isn't a shortest path, but because I don't know what it is yet. Okay? Now the rest of the algorithm is pretty simple. While some edge is tense, relax it. That's the whole algorithm. Okay? Find a tense edge, relax it. 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 Eventually, when you can't find any tense edges, you're done. So I'm not going to prove this to you, but there's a theorem that says if you follow this strategy, that at the end of this algorithm, you will have a shortest path tree. The distances will be correct, and the predecessors will, in fact, be point you to the second to last vertex on your shortest path. Okay? So there's this nice, generic algorithm for computing shortest paths. It makes no assumptions about edges being positive. It does make an assumption about edges not finding any negative cycles. And can anybody suggest why that might be true? So here, let me, just to get you started, let me create a nice little graph here. And ask you, what do you think would happen if you ran this algorithm on this graph? Okay, so I'm going to start off like this. Now you'll notice right away, this edge from S to A is tense. Because A thinks it's infinitely far away from S, and the edge is saying, no, you're only one step away from S. Okay, so I should relax this edge from S to A and change this to a 1. Now this edge from A to B is tense. It wasn't tense before, because infinity plus 2 is still infinity, but now it is tense because 1 plus 2 is considerably less than infinity. Right? And so, great, I found another tense edge. I should relax it. The predecessor of B should be A. Now this distance is 3. But now the edge from B to S is tense, because 3 minus 4 is less than 0. So I should relax it. But now the edge from S to A is tense, because minus 1 plus 1 is less than 1. So I should relax it. Right? So a negative cycle in the graph is going to make this algorithm run into an infinite loop. This is why we don't like negative cycles, or one of the reasons we don't like negative cycles. Okay. Depending on your strategy for finding these tense edges, there are ways of breaking out of the infinite loop. You can say, oh, I know this algorithm will only run in n cubed time if there are no negative edges. You've already run for 5n cubed time. You must be stuck in an infinite loop. Stop. Right? That's really actually how it's done. But that complicates the algorithm. I don't want to think about that. Okay. So this generic shortest path strategy was first described by Lester Ford in the early 1950s, more or less at the same time that the 1950s were a weird time because this was when all graph algorithms that we teach you were developed. And most of them, I shouldn't say all because Borufka was from the 20s, but most of the ones that show up in the textbook. And it's strange because they all happened inside government think tanks. Bellman, who when he came up with dynamic programming in the 1950s, working at the Air Force Research Lab, was doing it because he was working for the military, who was, rebuilding after World War II, and there was this Cold War stuff. We were all, hiding under our desks because everyone knows that a small layer of laminated plywood will protect you from the atomic bomb. All the basic stuff was done in the span of about 5 years between roughly 1952 and 1958, right? And sort of amazing that most of the algorithms that we teach you come from this small sliver of only 5 years. Partly that's because all the algorithms that were in my algorithms textbook came from that sliver of 5 years, because the people who wrote that algorithms textbook learned it from people who, the usual tradition argument. But really, it really was kind of a, laying the groundwork for more complicated things that you can hear me talk about next semester. Okay. So this is a great sort of meta strategy, but without some guidance, without some decisions about what order to look, how to find tense edges, what order to look for them, it doesn't really give you an algorithm. So in the notes, I sort of turn this strategy into a sort of generic-looking algorithm, which looks a lot like whatever first search. This is, whatever first shortest paths. I do the initialization, and then whenever I discover a vertex that I think its outgoing edges might be tense, I put it into a bag, so starting with S. I take vertices out of the bag, and I see if their outgoing edges are tense. If they are, I relax the edge, and then I put the other vertex at the other end back into the bag. Okay, this looks pretty familiar if you're used to thinking about whatever first search. What's a little bit weird about it is that the same vertex might be put into the bag multiple times, which is not true for whatever first search. Because I might legitimately discover that an edge is tense, and then I relax it, and then later I discover it's tense again, and I relax it again. Not because I'm stuck in an infinite loop, because it can just happen that way. And there are a bunch of things that you can plug in to use as the bag. The natural examples that you would probably try, well, let me just ask. I want a data structure that I can put things in and take things out. A queue. A stack. Good. These are both reasonable choices, except that they both suck. A stack will work. They'll work. They'll give you correct shortest path algorithms. But even if all of the edge weights are positive, if you use a stack, the resulting algorithm, although correct, may require exponential time. You may find yourself, in effect, considering all possible paths from S to one of the vertices. In fact, the worst case example is a DAG that has an edge, you number the vertices from 1 to n, and if I is less than j, there's an edge from I to j, right? And so you may end up trying all of the exponentially many paths from vertex 1 to vertex n. It's not exactly what you're doing, but that's what the worst case behavior looks like. And the 2 to the n ends up, it looks almost like the Tower of Hanoi problem. Bad. You don't want to do that. If you use a queue, you end up with an algorithm that's equivalent to what's known as Bellman-Ford. But developing the algorithm that way is not really the right way to think about Bellman-Ford. I rather think about Bellman-Ford as a dynamic programming algorithm. And that'll be all right. It's in fact the best general purpose algorithm when you have some negative edges. But when you have all positive edges, the right thing to do is to use a priority queue. And then it's Dijkstra. This is Dijkstra's algorithm. The only difference is, instead of bag, I use a priority queue. And does anybody care to tell me what the priority for a vertex might be? What number might you associate with a vertex when you're computing shortest paths? Distance. That distance value that we're computing, that's the priority that we use in the priority queue. Initially, everybody has infinite priority except the source, which is priority 0. And the priority queue gives you the thing where the priority is smallest. Now, as always, when this thing comes up, I have to complain about English. People talk about priority in two different ways. You say you have first priority, second priority, third priority. But you also have higher priority and lower priority. So first priority means higher priority than second priority, which is lower, even though 1 is lower than 2. I'm going to try to be very, very picky about this. I'm going to say larger priority and smaller priority, which really just means larger and smaller distances. But watch yourself when you start talking about priority queues, that you don't fall into this trap, that the English metaphors for priorities are utterly inconsistent. And you end up, doing exactly the opposite of what you think you're doing. So that's what Dijkstra's algorithm is. Dijkstra's algorithm is this sort of generic, whatever, but you throw a priority queue in as your data structure. Okay. Now, the other way that people think about Dijkstra's algorithm is as a greedy algorithm. Right? And the way that you want to think about, this greedy algorithm is as you're going along, Dijkstra's algorithm sort of computes the tree in a wave coming out from the source. And as long as all the vertices have, all the edges, have positive weight, then that actually guarantees that I'm going to pull every vertex out of the bag only once. And therefore, when I pull the vertex out of the bag, its distance is going to be correct, because I know that the generic algorithm gives me the correct thing. But I prove this in a different way. So I'm going to imagine that by the inductive hypothesis, I've already computed part of the shortest path tree to S. And so there are nodes where I already have shortest paths going out to those nodes. And then there are a bunch of things that are sitting in the priority queue waiting to possibly be added to the tree. Right? Now, if I think about this as a standard sort of backtracking problem, the question that I might ask is, I need to find one edge to glue onto this tree that will make it bigger and still be consistent with the shortest paths. Which edge should I pick? And if I think of this as a backtracking thing, the correct answer at that point is, I don't know, try them all. Right? So I'd literally try every edge coming out of the vertices whose shortest paths I already know, and then recursively figuring out how to grow the tree from there, and eventually, out of all those choices, which one turned out to be the best. Okay? What Dijkstra's algorithm says is, let's say the distances look like this. That just by looking at the distances, without doing any recursive backtracking at all, this is the one that I want to connect to the tree next. And I want to connect it based on whoever was, when I updated the distance to be 4, I did it by relaxing an edge. And so there's a predecessor pointer waiting for me that I've been updating as I updated the distance. This has got to be the right one. Okay, that's a great greedy strategy. I'm not going to determine recursively which edge is correct. I'm going to make a local decision based on the distances that I've computed, instead of making a global recursive decision based on just trying everything. So I have to convince you that this choice is actually correct, because greedy algorithms don't work. until you unload them yourself. I mean, until you prove them correct. Okay? So the claim is that this edge is in the single source shortest path tree. Okay? And this is the edge leading to the vertex that's not already in the tree that has smallest priority. Okay? So as usual, I'm going to say, suppose otherwise. Suppose that there is a shortest path tree that does not include that edge to the vertex going, well, let's give this vertex a name. This is vertex V. Okay? Well, the actual shortest path tree needs to have some path to V. Otherwise, it's not really a shortest path tree. At some point, that shortest path has to leave the part of the tree that my algorithm has already computed for a node outside that part of the tree. Here. Now, I'm working under the assumption, because Dijkstra assumes this, that all my edge weights are at least non-negative. Now notice, whatever vertex I went to here, this green edge, the first non-blue edge in the shortest path to V, it had to go to a vertex whose distance value was bigger than V, because otherwise it would be the edge that I'm trying to claim is not there. And so the basic conclusion is that this distance is actually going to be 12, which means that this distance is actually going to be greater than 12, which is wrong. Okay? If I go through an edge to a vertex that's further away, then I'm creating a longer path to V, which means that this path couldn't have come from a shortest path tree. Right? In other words, if I try to build a shortest path tree that doesn't include this edge going to V, I end up deriving a contradiction, because in that other tree, the path to V is longer than the one I want to build with the greedy algorithm. By doing this exchanging the solid green arrow for the orange one, I made the shortest path, I made the tree better. Okay? Yes?
So I realized that, like,
Mm-hmm.
wouldn't Dijkstra's algorithm still...
Okay, so this is a good point. What happens when, right now I'm just assuming that edges are non-negative. Because only in this circumstance is Dijkstra really a greedy algorithm. Right? When all the edges are positive, the distances can only grow as you get further away from the source. Right? So think of it as this expanding wave. So once I make a decision, hey, I'm going to glue this vertex onto the tree, that decision is irrevocable. So from that point on, I'm only going to consider things that are further out. I don't have an opportunity to decrease my distance anymore. If I have negative edges in the graph, then any decisions I make about gluing things onto the tree are contingent. They might change, because there might be this path might actually have negative weight, which means this green path might actually be the right one. Yeah? Again, it depends on precisely how you write Dijkstra's algorithm. If you write Dijkstra's algorithm by saying, I'm going to put all the vertices in the priority queue, when I do a relaxation, I'm going to do a decrease key. When I pull things out of the priority queue, they're never going back in. Right? Then you're already assuming that I'm only going to pull things out of the priority queue once, which means that version of Dijkstra's algorithm will only be correct if all the edge weights are positive. If you write Dijkstra's algorithm this way, whereas you discover, hey, I relax this edge, then put the vertex at the other end into the priority queue, it will be no less efficient, but it has the advantage of actually being correct, even when some edges may be negative. On the other hand, it might run an exponential time when the edges are negative, which means, from a theoretical standpoint, Dijkstra's not so great, even it's right. Exponential time incorrect is better than fast but wrong, but it's still not the choice that you actually really want, which is fast and right. Okay? So, just to sum up, the right way to sort of sum up this algorithm is it's closest first search, in the sense that you do depth first search by just sticking things into a stack. You do breadth first search by sticking things into a queue. Yarnick's algorithm for minimum spanning trees is lightest first search. You build a priority queue where the priority is the weight of the edge. You grow the tree out, the spanning tree out that way. This is closest first search. You use a priority queue to guide the traversal of the graph, where the priority of a node is the distance you've computed for that node. Okay. If all the edge weights are non-negative, then I have so each node leaves the priority queue at most once, and I may end up doing a priority queue operation for each edge. So I have one priority queue operation, at most one priority queue operation per edge. Either check to see if this edge is tense, and if it is, relax the edge and do a decrease key on the head, or check to see if this edge is tense, and if it is, insert that head vertex into the priority queue. Either way, every time you relax an edge, you need to do something in the priority queue, but you're only going to do that once for each edge. And so in the end, the running time is going to be E log V, because I have E operations on a priority queue containing V things. Right? If some edges can be negative, the running time is horrible, in theory. In practice, people have done experiments, people have done large-scale computations of shortest paths using road networks and so on, injecting some negative edges in there. In practice, actually, Dijkstra works pretty well. You can make it run in exponential time, but only by very tightly engineering the graph to be bad. If you really run this on just a normal graph that has a few negative edges sprinkled in, Dijkstra's fine. Dijkstra's, in fact, better than other things like Bellman-Ford, which is one of the reasons why I will insist that Dijkstra described Dijkstra's algorithm incorrectly, that you shouldn't assume that the priority queue, every vertex is going to come out of the priority queue only once. If you write it in this more generic form, it will still work, and it will likely be the right algorithm, even if there are negative edges. Okay. Yes? Okay, I have E priority queue operations. Every time I look at an edge, I might relax it, and when I relax it, I have to either put a vertex into the priority queue or change its priority. But the priority queue contains vertices. There are most V things in the priority queue. So for example, if I use a binary heap as my priority queue, each operation will take log V time. Okay. All right, so that's greedy, or using a priority queue. Let me describe a different algorithm, which everyone calls Bellman-Ford, but of course it was really discovered by someone else first. So Schimble's algorithm. I'm just going to describe to you what it is first in a way that will be easy to implement. In fact, it's easier to implement than Dijkstra's algorithm. It's not quite as fast. There it is. Look at every edge. If it's tense, relax it. Are you done? I don't know. Look at every edge. If any of them are tense, relax them. Are you done? I don't know. Look at every edge. All right? So you just literally, repeatedly scan through the entire graph, and anytime you see a tense edge, you relax it. And if you manage to make a complete pass through the graph without ever finding a tense edge, you're done. Because I know that when none of the edges are tense, I've computed my shortest path tree. Okay? Now, the part of this algorithm that is a little bit non-trivial to justify is that if there are no negative cycles in the graph, I mean, I know if there are negative cycles in the graph, this algorithm would never terminate. There would always be another tense edge. So the thing that I have to actually convince you of is that if there are no negative cycles, then after V passes through the graph, I will be done. Okay? This is not in any way obvious why there should be this upper bound on how many times I pass through the graph, especially since I've already told you two other algorithms that can be forced to run in exponential time. I could use a stack, or I could use Dijkstra when the edges are negative. I'm actually making a very strong claim here that I can, under the worst of possible circumstances, I have an algorithm that runs in order V times E time. I just repeat V times, look at every edge. Okay, how many of you think you could implement this, right? I would hope that the rest of you have your hands down because you're asleep, not because you don't think you could implement this. I mean, it's 10 lines of code, right? I would be, I would actually be comfortable if I knew that everyone would have, some sort of development system on their desk saying at a midterm, implement this algorithm. You have 10 minutes. Honestly, 3/4 of the class would be done in 5. Okay, there's the pseudocode, right? I told you relax, that's 2 lines. Initialize SSSP, okay, that's 2 for loops. Right? I'll give you the graph library so that you have a data structure. Right? Right? Simple. So how do I know this actually works? How do I know that V times through the graph is enough? Well, the way that Bellman did this, not surprisingly, since Bellman was the person who coined the phrase dynamic programming, is he said, hey, this is a perfect example of a dynamic programming problem. What I should do is write down a recurrence for the distance from one vertex to another. So let's define, what is the distance? This is going to be the shortest path distance from S to V. Let's try to come up with a recurrence for this. Okay, good. I need to. All right, let's try to come up with a recurrence for this. All right. Anyone want to suggest a base case? Right. So if the vertex I'm trying to get to is the source, then the distance is 0. Right? The only way I could possibly get less than 0 is if there was a negative cycle that went through S. Right? But I'm assuming there are no negative cycles. Otherwise, well, I have a choice. Right? I'm looking at the length of the shortest path. Wait, a path. That's a sequence of edges. So the single question that I might want to ask is, what's the first edge in this sequence, or what's the last edge in this sequence? But because I'm fixing the source vertex S, it probably makes sense to ask what's the last edge in the sequence, and then what's the shortest path from S to that second to last vertex. So I might imagine something like, this is the minimum over all possible edges that lead into V of the distance to U plus the weight of this edge from U to V. It's otherwise. Right? This is correct. This equation is correct. It is correct that the distance to V is the minimum over all incoming edges of the distance to U plus the weight of that edge. And the particular U that I want to use will be the predecessor that I'm trying to compute. Okay? So it's correct as an equation, but it's not correct as a recursive definition of distance. Why not? What would happen if I just implemented that as a recursive algorithm? Sorry? Well, if there's nothing to go into V, in that case, correctly, you're taking the minimum over the empty set and getting infinity. If there are no edges going into V, then it's infinitely far from the source. That's not the problem. Let's look at, this simple graph again. In fact, let me do this. Okay, so if I want to compute the shortest path to A, I have to compare the length of this edge plus the distance at S, and the length of this edge plus the distance to C. So I need to compute the shortest distance to C. But in order to do that, I have to compute the shortest path to B. But in order to do that, I have to compute the length of the shortest path to A. But in order to do that, I have to compute the length of the shortest path to C. I'm stuck in an infinite loop. And it's not because there's a negative cycle. It's because when I recurse, nothing went down. Right? Remember, in order to get a recurrence that actually works, in order for the recursive algorithm to bottom out, you somehow have to be getting closer to the base case whenever you recurse. And I'm not doing that. Okay? I'm just wandering around in the graph, and so I'm going to end up falling into an infinite loop. So I need to impose something that gets smaller. I need some way of arguing that when I recurse, I'm getting closer to the base case. And the way that Bellman decided to do this is he introduced a second parameter into the recurrence. All right, so this is the length of the shortest path. Right? I'm just expanding the definition of distance. But it's not the shortest over all paths. This is the length of the shortest path from S to V with, at most, I edges. Okay? So distance sub 1 means the shortest path that consists of at most one edge. Distance sub 5 means the length of the shortest path that is composed of at most 5 edges. Okay? So this gives me a second base case for the recurrence. The distance sub 0 is the shortest path that doesn't use any edges. This is only going to be well defined if the vertex that I'm trying to get to is S, because the only path from S that doesn't have any edges ends at S. Okay? So there's a second base case now, which says that if I want to get to any other vertex in 0 steps, I can't. I'm going to make that distance be infinity. Okay? Now, in the general case, there are actually 2 options. One of which is related to this recurrence on the bottom. It could be that the shortest path that uses at most I edges actually uses I edges, uses all the budget that I'm given. In which case, I should look for the last edge and then look for the shortest path leading up to U that uses at most I minus 1 edges. Okay. I've got I edges all together. I want to pick out the best last edge and then recursively find the other I minus 1. But the other thing that might happen is the shortest path using at most I edges actually uses less. So in this graph up here at the top right, if you imagine all those edges have weight 1, the shortest path from S to A that uses 25 edges or less actually only uses 1 edge. So it's in fact equal to the shortest path from S to A that uses 24 edges or less. Okay. All right, so we end up with a recurrence that looks like this. Distance sub I is out of all paths from S to V that use at most I edges, which one is shortest? If I is 0 and I'm trying to get to S, well, then I do it in 0 steps, and then I have a total distance of 0. If I is 0 and I'm trying to get it somewhere other than S, I can't do it at all, so I should just put in this target value infinity. And in the generic case, there are 2 possibilities. Either I don't really need to use my entire budget of edges, in which case dist I is the same as dist I minus 1. Or I need to recursively, I need to consider all possible last edges along this path. And then recursively ask, how do I get to U using 1 less edge? And then how do I glue on the last edge from U to V? Okay? This is an actual proper recurrence, because every time this distance function calls itself recursively, that argument I goes down. And when it goes down to 0, the recurrence bottoms out at the base case. Now the nice thing is, I know that something about that index I is that it can't be arbitrarily big. The shortest path goes through every vertex at most once. So the true shortest path distance is distance sub number of vertices. Right? So what I'm actually trying to compute is dist sub capital V of every node. Right? So here's a recurrence. How would you memorize it? A 2D array. How do you index the array? There are these 2 parameters to the recurrence, I and V. I've written I as a subscript, but that's notation. It's really 2 arguments, dist of I comma V. Right? So I have a 2-dimensional array indexed both ways by the vertices. Because I ranges from 0 to v, and v ranges over the vertices explicitly. Okay? Now, the evaluation order for this 2D array is pretty clear because every dist IV depends on dist I minus 1 something. So the outer loop I should consider an increasing order of I. And then for every v in here, I've got this loop over the edges coming into v. So for each possible value of I, and for each vertex, I'm going to look at all the edges coming into that vertex. Right? And so I'm going to end up with an algorithm that looks like this. But if you have two nested loops, say, notice here inside the main loop, it says for every vertex and then for every edge going into that vertex. That is exactly the same as saying for every edge in the entire graph, just in a particular order, right? I've decided that the order in which I'm going to look at the vertices is first I'm going to consider all possible heads, and then I'm going to consider all possible tails in sort of in two nested loops. But I don't really need to specify that order for the algorithm to be correct, right? So I can, get rid of that distinction and just say in the second loop, after I've done the initialization, just for every edge, evaluate the recurrence. See if my guess for that max in this recurrence here, right? I'm going to have some guess for what I think distance of I is going to be, and I'm going to compare that guess for distance of I to this choice for what it might be, and whichever one is smaller, I'm going to accept that as a better guess for distance of I. And so what I'm going to end up with is code that looks like this. Okay? Now, if you look at this loop, what is that loop actually saying? It's saying for every edge, if the distance to v is bigger than the distance to u plus the weight of the edge from u to v, update the distance to v. That orange box says, for every edge, if it's tense, relax it. Okay? The other thing to notice is that I don't actually need to carry the first index of the table around. I needed to do it to develop the dynamic programming recurrence in the first place. But then the observation is, if I just keep one distance for every vertex instead of an array of distance for every vertices, the worst thing that could possibly happen is that I relax things faster than I would by following the dynamic programming in lockstep. Relaxing things faster is fine, as long as all I'm doing is this inner loop of see if it's tense, if it is, relax it. Doing things slightly out of order isn't going to actually make any difference. And so I can just do that. I'm going to, in fact, only memorize it into a one-dimensional array. Or an even better way of thinking of it is I'm just going to store a vertex at every node in the graph, a distance at every node in the graph. And now the dynamic programming algorithm simplifies even more, because I'm not even carrying around a two-dimensional array anymore. And in this form, it is exactly what the algorithm that I showed you before. Initialize, and then v minus 1 times, look at every edge. If it's tense, relax it. Okay? And that's why we know that v iterations of this loop are enough. Essentially, the reason is it comes out of a recurrence that Bellman was smart enough to come up with. And that v is actually the number of edges that might be in the shortest path. Every time you make a new pass through the graph, you're considering paths with more edges. And you're accepting them as being better if their length is shorter. There's this tension between the number of edges in the path and the sum of their weights. So in short, you're looking, every time you pass through the main loop in Bellman-Ford, you're looking at longer but shorter paths. Longer paths because they have more edges, but shorter because they have less total length. And eventually you consider paths that are as long as they could possibly be, and then you're done. Okay? So this is what you would actually implement. And again, given that you have a data structure to do graphs, I'd be shocked if this took anyone more than about 10 minutes to implement, because it's just a pair of nested for loops. Okay, now there are other things that I would love to be able to talk about. In particular, I haven't really spent any time talking about all pair shortest paths. The one thing that I want to point out is that in the notes there is a different algorithm than run Dijkstra at every source or run Bellman-Ford at every source that actually runs in n-cube time. It's called Floyd-Warshall. It looks like this. It's 3 nested loops instead of 2 because you actually have a recurrence with 3 arguments. But it's pretty simple. This will run in v-cubed time. And this is also essentially the algorithm that you would use if you wanted to transform a DFA into a regular expression. If you want to think of it this way, a regular expression is really encoding all possible ways of walking through the DFA from the start state to one of the accepting states. So what this Floyd-Warshall recurrence allows you to do is not explicitly, but in some sort of implicit sense, think about all possible paths from S to everyone else and pick the shortest one. Now, I want to emphasize that, even though, so here's the algorithm to turn a DFA into a regular expression. I don't expect you to know this on the exam. The one last thing that I want to say about these things, there's an extraordinarily common mistake that people make, and they make especially under time pressure in exams. Sometimes you'll face with an exam problem where you want to find the best path between 2 nodes. One way that you can do that is, let's consider all possible paths between these 2 nodes and pick the best one. That's perfectly correct. None of the algorithms that I've shown you do that. Depth first search does not consider all paths. Bellman-Ford does not consider all paths. Dijkstra does not consider all paths. If it did, they'd all run in exponential time because they're an exponential number of paths. Okay? There's sort of an implicit sense in which they consider all paths by considering all subpaths and gluing them together. But that's not really what's going on, and that's not really the right way to think about it. The way that you want to think about these things on exams is always, I need to build the graph. What are the vertices? What are the edges? The edges might have weights on them. What are the weights? The edges might be directed or not. Which is it? And then, what problem do I want to solve? Do I want to solve shortest paths? Do I want to do topological sort? Do I want to do minimum spanning tree? And then say, oh, under these circumstances, use this black box algorithm. We're out of time, but if there are any questions, I'm happy to answer. Thanks.
Two questions and a concern.
Yeah.
So when you did the